section, that is also we call as the best hydraulic section. For rectangular section, now we can see what is the value of, say, hydraulic radius. What is the value of hydraulic radius? Because why it is required? Say we require the, for calculating the discharge amount, we require the hydraulic radius also. So once we can have the hydraulic radius in terms of depth, then also we can do those calculations. So let us just see what is the value of hydraulic radius in most economic section, that is R is equal to A by B, and now we can write that area is equal to B into Y, and then perimeter is equal to B plus twice Y. But what this B is, this for best hydraulic section, we have we have R is equal to, say, in place of B, now we can write twice Y, because B is equal to twice Y. So we can write B into Y, then twice Y plus twice Y. So this will lead to twice Y square by 4Y, or this is equal to Y by 2. So R is equal to Y by 2. That is what the best hydraulic section, and in best hydraulic section, hydraulic radius can be considered as R equal to Y by 2. Well, with this understanding of best hydraulic section, now let us see whether this same concept or the same relation will remain valid for other sort of channel. Well, let us discuss about trapezoidal section. Well, if we take a trapezoidal section of this sort, say this is Z, side slope is Z, and let us consider this to be symmetrical. Generally, when it is man-made, we will generally try to make symmetrical. Of course, in some case in hills, we may go for unsymmetrical also. If one side we have slope, other side we do not have, then we may go for suppose a unsymmetrical channel also. It may require, but normally we try to go for a symmetrical section. Say depth is Y. Well, now in case of trapezoidal section, we can write that area is equal to, say, B plus ZY into Y. That expression we already know, and this will lead to say B is equal to, say, A by Y minus ZY. Okay, that's why we are getting the that way we are getting the expression for B. Okay, and then perimeter is equal to, we can write B plus twice Y root over 1 plus Z squared. Okay, now this can be written as P is equal to, in place of B we can write A by Y minus ZY, that means just writing the B value, plus twice Y root over 1 plus Z squared. Now if you just apply the same condition that for best hydraulic section, dP dy is equal to 0, that implies dP dy is equal to, we can write, that is minus A by Y squared. Y differentiating, so it is, and A we are considering as constant here. Then this will be minus Z, and then plus 2 root over 1 plus Z squared. Well, so this is equal to 0, and this implies that twice root over 1 plus Z squared, that expression I am writing with an intention here in this side, is equal to A by Y squared plus Z. Now we can again replace the value of A. We know that A is equal to B plus ZY into Y. Okay, so what we can write, that is 2 root over 1 plus Z squared is equal to, that was a by y square. So in place of a, we can write now this as b plus zy into y. If we just recall, this was a. So a we are replacing by this, by y square, and plus z. So this way we are writing this expression. Fine. And then if we multiply this by y, then let us see how we can write. Say twice y root over 1 plus z square. Twice y root over 1 plus z square is equal to, this is already going, and then it becomes b plus zy plus z into y. b plus zy plus z into y. Or we can write this as, say, y root over 1 plus z square. Y root over 1 plus z square is equal to half of say b plus twice zy. b plus twice zy. Now if I draw the trapezoidal section here, this is leading us to one important aspect. Say this width is b, fine. The side slope is z, already explained. Now this height is y, this depth is y, this depth is y. Fine. So what about this side? Say from here to here, this is zy. Okay. Now, so what is the length of this side? What is the length of this side? If this is y, this is zy, then it will be root over, that is simply applying this square plus that square is equal to the diagonal, two perpendicular sides. So this length is nothing but y square plus say z square y square root over. So we can write this as y root over 1 plus z square. So this part is giving us the side length. And then we know that this part is b, and this is again zy. This is again zy. So what is half of b plus twice zy? b plus twice zy is nothing but the top width, t. So half of b plus twice zy is nothing but, say, half of the top width, means from here to here. So this length is equal to that length. And this is what the condition for best hydraulic section. We can write that length of inclined side is equal to half of the top width. So that way, this is leading us to this condition. So if a trapezoidal channel we want to make most economic, we'll have to design it by following this concept. Again, we should not forget that there may be a lot of practical consideration which may not allow us to have this sort of best hydraulic section. Well, we have discussed about the design concept of line canal. We have discussed about the design concept of line canal, and of course discuss some of the fundamental aspect of, say, unlined canal also. But we are yet to cover that if the channel is, suppose it is a line canal but it is triangular, it is circular, what will happen? How we'll design that part? So that we'll be discussing in the next class, and then along with that we'll be starting our discussion on unlined canal as well. Thank you very much. Friends, welcome you all to this class of canal design. which we'll be continuing today. We started on canal design yesterday, and we'll be continuing with this class today again. What we were discussing on canal design, let us just recapitulate. We started with the very fundamental concept of design of channel, and then at that point we did discuss that channel may be line canal or it can be unlined canal. Well, now when it is line canal, then we could see that the problem of scouring or say erosion is not there. As such, our design concept is different, or rather we try to make the channel in a most economic way. And then when we talk about unlined canal, then our problem are different. There it can be non-alluvial, the channel, I mean within the unlined category itself, there can be non-alluvial channel or the channel can be alluvial channel. Well, when it is non-alluvial channel, then again we could see that a problem of erosion is not there up to a certain limit of velocity, and problem of sedimentation is of course not there, because we consider that in a non-alluvial channel the sediment carried by the water is less, and as such the sedimentation problem is not there. However, the erosion problem, as I said, that it is not there up to a certain limit, then we should maintain up to that limit of velocity. That means our design principle becomes such that we should decide our shape, we should design our shape of the channel, we should design our size of the channel in a way that the flow velocity does not exceed that permissible limit. That is maximum permissible velocity concept come there. And when we talk about alluvial channel, then the problem can be both scouring, that is the erosion of the bed and bank, and the problem can be of sedimentation. So that way, we just need to take care of both the cases, and it is very difficult to have analytical solution for such problem. And then generally people try to have the channel of the size so that a velocity is achieved which is referred as critical velocity. That critical velocity is that this velocity, or under this velocity, the channel will neither be eroded nor there will be a deposition, so or sedimentation. So that sort of critical velocity how we can have, that is again a very challenging task, and for that purpose generally empirical relations are used. Means the equation derived on the basis of lot of observed data of such stable channel that are used. And of course, some semi-empirical theory are there, like tractive force method, and that are also applied. Well, and in the last class, we could see that design principles are different for different type of channel, and design principle for line canal is to have the best hydraulic section, and we started with the design of a rectangular channel, and then we could complete up to trapezoidal channel. Well, then again we tried to see that in trapezoidal channel the design criteria is that or the best hydraulic section is that one where the length of the side channel, length of the side slope is equal to half of the top width. That was the condition that we could derive. And using that condition, again, we can see that for a trapezoidal channel, when it is the best section, best hydraulic section or most economic section, it is satisfying this particular condition, what we have stated, then it can be found that hydraulic radius R for that situation is equal to half of the depth. That is R is equal to Y by 2. And the same condition we could see for a rectangular channel as well. And in rectangular channel, the condition for most efficient section, we are using several terms, a most efficient section, best hydraulic section, or say most economic section. In fact, all are meaning the same thing, that is the perimeter minimum. And for rectangular section, we could see that B, that is the bed width, is equal to twice that of the depth. So that was the condition for best hydraulic section. And of course, we have already explained what is the condition for trapezoidal section. Now let us see what will be the condition for triangular section. We'll start with that. Well, now let me take a triangular section. Well, say this is a triangular channel and this is the depth of flow. And let me just call this angle as theta. And of course, we can just give idea about this theta in terms of the side slope also, that is z:1. It can be written from as theta or z:1. And depth of flow in triangular section is y. Okay. Now let us see what is the expression for area. Area is equal to half of the base into altitude. Now what this base is basically, as we know that this top width is equal to z into y this much, and again z into y this much, because depth is 1. And so the top width we can write as, say, twice z into y, twice z into y. So our expression for area is half of the base into altitude. So this is what the base, and altitude is y, and I mean this height is y. So that is equal to zy square, and that will lead us to an expression for y is equal to root over a by z. Well, as now we know that our concept of making a design for most economic section is that we will try to make the perimeter minimum, that is P. If we get an expression for P, we will try to make P minimum. And in that case, earlier we were doing dP dy, that is with the change of y, how the P is varying, and we are trying to see that when dP dy is equal to 0, that will give us the expression for minimum value of P. Now here we can see, of course, y we could change, but if we change the z, if we flatten the z, if we bring the z here, depth will automatically come down, or perimeter. So for a given area, if we change the z value, depth will come down. If we increase the depth, if we reduce the z value, it will be coming like this. Or rather, if we increase the z value, it will be coming like this. If we decrease the z value, it will be going like this. And then the depth of flow will be changing, and then perimeter will also be changing. Weighted perimeter will also be changing. So we can see, and for design of a triangular section, what we can specify, that suppose we are asked to design a triangular section, then we can specify that, well, this should be the area and this should be the side slope. Once we specify the side slope, because here B we need not specify, B is not coming at all. So B means bed width I am talking about. So we need to specify the side slope. Well, so we can see that when P will be minimum in terms of Z also, there is a variation of P perimeter with respect to Z, we can say. So we can try to find what is dP dZ, and that way we can try to equate this to equal to 0. So this way, let us see what is the expression for P, and perimeter P. Let me write the expression for perimeter P. That perimeter P is equal to, say, this length is equal to y root over 1 plus z square. That means this part is root over, say, this length is, if it is 1, it is z root over 1 plus z square. So this will be, this total length will be, for one depth it is like that, for y it is root over, say, 1 plus z square, and then we'll have to multiply it by y. So this is the perimeter, and this perimeter, this is only one side. So but we have perimeter means we have both the side, this and that. So it will be equal to 2 times of y root over 1 plus z square. And that can be written as 2 times of this y. Now we will be expressing as root over a by z. And then we can write this as root over 1 plus z square. Well, and this can be written as, again, say if we take this z inside this root sign, then we can write it as twice root over a and root over 1 by z plus z. Well, now to have this expression in a simple form, we can square the both sides. So squaring, what we can have, squaring this equation, squaring the above equation, what we can have, we can write this as p square is equal to, say, 4a then 1 by z plus z. Now we can do differentiation of this equation with respect to z. So differentiating with respect to z, what we will be getting, this is, say, twice p, then it is dp dz, and our interest is that this should become 0, is equal to 4a, and then this expression will become, this is, I am writing first dz is equal to 1, and this will become, say, minus 1 by z square. This will become minus 1 by z square. Well, if dp dz equal to 0, so dp dz equal to 0 implies, now from this expression what we can have, so this is 0 means, this left hand side is 0 means we have that 4a 1 minus 1 by z square is equal to 0. And now in a channel, if area is 0, there will be no flow. So the question cannot be let area, whether area will become 0 or not. This is a product of this and that item. So this term cannot become 0. And as such, this expression must be equal to 0. And so this implies that 1 minus 1 by z square is equal to 0. This implies 1 by z square is equal to 1, and 1 by z square can be equal to 1 only when z is equal to 1. And z is equal to 1 means what we are getting indirectly, that our z is equal to 1, 1. So this z is equal to 1. That means this angle theta, the angle theta must be equal to 45 degrees. So this implies theta is equal to 45 degrees. So a triangular section will be the best section when we can have theta is equal to 45 degree. Or theta 45 degree means when we talk about the total angle, then this is equal to 90 degree. So a 90 degree channel, we can say 90 degree channel means the angle of the triangular section should be 90 degree for this is to be most efficient. And of course, in practical situation, when we propose triangular channel, then it may not be possible to provide exactly a triangular channel, and then in many a time it is given like this, and this portion is rounded up, and then we provide these things like that. But the angle, if we extend, this should be, say, 45 degree and 45 degree like that. Well, then we can go to the another type of channel, that is circular channel. Okay,